Okay, hello everybody. How does U substitution help evaluate these integrals? And so, actually all of these should maybe be in blue because they might change a little bit on the exam, but the idea will be roughly the same. It'll just change a very small amount. So, U substitution. If we look at this function here, it's the function sending x to this formula. We don't know an antiderivative. If this was little f, we actually don't know capital F. We'd like to know capital F, but it's not entirely obvious what it is. Same here. We don't really know what capital F is. If we did, we could do capital F of 4 minus capital F of 0 by the fundamental theorem. But, so I guess I would say when you don't know an antiderivative, remember, so I'm using words in my answer, words, pictures, formulas. Here's my advice. Use a computer, because the computer will know it. It has tables built into it. It has all these different rules and patterns that it knows. And so you might as well just use a computer to find the antiderivative, and then you can use the fundamental theorem to just do the subtraction. Now, if there are no computers, for example, if you are in a spaceship and all your computers fail and you're just floating around and you just want to do an integral. I'm not sure. Actually, there'd probably be computers in your spaceship. Anyway, if there are no computers, try U substitution. So what does it do? What does U substitution do? It uses the change of volume factor, exactly what we've been learning about, the change of volume factor in one dimension to make an integral easier. Okay, that's what I have in words. Now let's see it in action. So all of these are things that we don't know the antiderivative to right off the top of our head. But if, let's say we were in, maybe I'll use a picture color. In the U world, so this was the X world. This was X equals 0 to X equals 2. We could view it as like 0 to 2. And we're integrating over this region. And that's X. But in the U world, we would like to integrate from somewhere to somewhere. And we'll have to figure out where that is. But basically, this integral will be U equals something to U equals something of U squared. And that's great because we look at this and we know the antiderivative is U to the third over 3. And so we know capital F, and we can plug in, and that's how it's going to go. So this is what we do. We say, what's this map here? I guess this map is U equals x squared plus 4. And now what people do is they write du equals 2x dx plus, and then the derivative of 4 is 0. And so that means that du over 2x is dx. Or in other words, the 2x dx, which appears right here, will be replaced by a du. And the x squared plus 4, which appears right here, will be replaced by u. Okay, so now what is this map? I guess it's the map, let's make it a little more clear. X goes to x squared plus 4. So that means that 0, x equals 0 and x equals 2. Let's see where they go. 0 and 2. 0 goes to, 0 squared plus 4 equals 4. 2 goes to 2 squared plus 4 equals 8. And so we're going to go from u equals 4 to u equals 8, and we'll integrate over this region. And we'll integrate from u equals 4 to u equals 8 of u squared du, because dx is du over 2x, which cancels that 2x. And this is really easy. It's just, well, u to the third over 3, evaluated at 8 and 4, which is just, this is a 3. Okay, that's the answer. This was the answer to even our original integral. So that's the idea of u substitution. What's happening here? What's happening here is the change of volume factor is being sort of hidden in the language of differential forms, which we do not understand in this class, but you will understand in an advanced calculus class. You'll understand differential forms. They're linear functions of a vector in this case. Dx is a linear function of a vector. And other differential forms even exist in higher dimensions. But basically, we've seen it is that this is accounting for the stretching. Obviously, a length 2 in the x became length 4 in the u. So clearly, this map has distorted volumes. And that volume distortion correction factor just got rid of this stuff and made our integral much easier. Okay, let's do another one. This time with less talking. So I wish this were a u, because u to the square root is u to the 1/2, and I know an antiderivative, I just add 1 and divide by the exponent. This is the antiderivative of the square root of u. Okay, so what do? I'm gonna go from the x world, from 0 to 4, and I'll send x. Where will x go? X will go to u. And in the u world, we'll go from somewhere to somewhere. Now, what will u be? Well, I'd like it to be 16 minus x squared. So I have to adjust the volumes by dividing by negative 2x. That's basically what I have to do in order to adjust for the distortion in volume. Now, what's a volume? A one-dimensional volume is a length. And so you can see that this length is 4. And over here, this length is, well, let's figure it out. 0 go, where does 0 go? 0 goes to 16 minus 0 squared, 16. And where does 4 go? 16 minus 4 squared. Well, that is 0. So actually, we're going to start at 16, and we're going to go all the way, so u equals 16 to u equals 0. So this is length 4, and this is length 16. And this way, we're going from 0 to 4. And now we're going to go from 16. So we're sort of reversing direction. That makes sense because look at, we have a minus x squared. U is equal to something minus x squared. So we're reversing directions, and that's okay. And now what happens? Well, we get a u to the 1/2, or a square root of u. And the dx gets replaced by du divided by negative 2x. So I had a 4x out here, and I have a du divided by negative 2x. And so this cancels and gives a negative 2. And basically, we get negative 2. Let's write square root of u by u to the 1/2. And we'll do this integral. So what's the antiderivative? The antiderivative is add 1 to the exponent, divide by that exponent. The negative 2 should hang out, and we should evaluate at 0, and then subtract what we get by evaluating at 16. So we get 0, 0 to the 3/2 over 3/2 times negative 2. And all of that is 0 minus, okay, minus what? Well, 16 gets placed right there. So 16 to the 3/2 over 3/2 minus 2 is multiplied. And so I guess minus times minus is a plus, and whatever, this is the answer. Okay. Square root of 16 is 4. 4 to the 3rd is something, and then you divide by 3/2 and then multiply by that, and then multiply by a negative. Anyway, Let's do another one. Okay, I wish this were a u to the third. U to the third would be easy to integrate. I just get u to the 4 over 4. Okay, well, so let's take our x world from 0 to 2 pi. And let's take x and map it to u equals cos of x. And then du equals, well, the derivative of cos is minus sine. And so I guess minus du is sine x dx. So I can replace sine x dx with minus du. So I get minus du, and that's going to be multiplied by u to the third. Okay, so I guess another way to say that is just the integral of minus u to the third du. Now what are the bounds? Well, interesting is that 0 and 2 pi, this is in the x world, and then in the u world, what will they become? Well, 0 gets mapped to the cosine of 0, which means u is 1. U equals 1. And what happens to the other endpoint, 2 pi, maps to the cosine of 2 pi, which is 1. So I'm going to integrate from u equals 1 to u equals 1, u to the third, and right away we can see that the answer is going to be 0, because there is nothing under there. Okay. Now, you have to be careful about u substitution, because you might think that, well, first of all, if you know this integral, then you can just do it. And what is it? 2 pi squared over 2 minus 0 squared over 2. So I guess the answer is 4 pi squared over 2, which is 2 pi squared. Okay, but if you were doing a u substitution, for example, this is the answer, this is correct. But if you go to math.stackexchange, you can find a nice discussion of this example about like u substitution and an error that you can make. So let's make the substitution u equals the sine of x. Okay, so du equals cos of x dx, blah, blah, blah. And let's take the bounds, x equals 0, x equals 2 pi, and let's map them over to u. And where are we in u space? Well, if x is 0, sine of x is 0, so u equals 0. If x is 2 pi, sine of x is 2 pi, so u equals 0 again. So can we then say that, since we're integrating from u equals 0 to u equals 0, something, yes, we'd have to figure out what this is, but do we really? Because this should just be 0. And we would be very, very wrong, because the answer is this. And so I guess, u substitution, if you don't understand what's happening, so if you want to understand, read math.stackexchange on this, and search something like u substitution incorrect, or u substitution error, and you'll find a very interesting discussion of this explained. But you have to be careful about doing things you don't understand. So things like I don't know, like in all these problems we're like sort of just doing stuff and we don't really know what's happening, and somehow we get the answer. If you're gonna do that, you might as well just use a computer. So I guess that's my little word of warning. Until you understand differential forms and the theorems that make these sort of tricks work, it's maybe a better idea to use a computer to find antiderivatives. And the computer will most likely not make a mistake. You have to tell the computer to do the correct integral for your scientific problem, which means you do need to understand what is an integral. But you already know what is an antiderivative. You know what it is, you understand it. You just need help finding it. And there is no great way to do that. So just use a computer.